Welcome friends, in this new video we will see the comparison test. Using the comparison test, it is given two series and how they are related. Convergence of one series. Using the convergence of one series we can show how the second series is also convergence, and whenever one series is divergent, if there is a relation in the terms of the series, and if one series is a divergent, then the second is also a divergent. So this is the main part of the comparison series in the discussion. Now I am going to write here the statement of the comparison test. This is the comparison test of first type. Here, if summation un and summation vn are are two positive are two positive terms are two positive terms series are two positive term series and k not equal to 0. This is a very important number. K not equal to 0, a fixed positive real number and there exists a positive integer m such that and there exists a positive integer m such that un less than equal to k into vn for all n greater than equal to m. Then number one part, if summation un is convergent, if summation vn is convergent, and second part of this, summation vn is divergent if summation un is divergent. So friend, it is given that how the terms of the series are related, and we know that to show the convergence of a series we know their sequence of partial sums. So here first we take a two sequences of partial sum. So let us suppose that Sn equal to u1 plus u2 plus un and Tn equal to v1 plus v2 plus vn. These are the B sequences. These are the sequences of partial sums of two series of summation un and summation vn respectively. Okay. Now for all n greater than equal to m, we have, you can see that here Sn minus Sm equal to what we get, um plus 1 plus um plus 2 plus here un. Okay, but we know that this um plus 1 is less than or equal to k into vn plus vm plus 1 plus k into vm plus 2 plus k into vn. So this is equal to k into tn minus tm. This is the relation which we get. Now it is given that summation Vn, now first see here, if we take first condition, summation Vn is convergent. If summation Vn is a convergent, then we can apply the Cauchy's criteria, that means Tn minus Tm is a less than epsilon by 2, or Tn is a bounded terms. So Vn is convergent, so its partial sum is also bounded. Now Vn is convergent, so sequence Tn is a bounded. If Tn is a bounded, that means Tn is less than equal to capital B for all n. And then here the relation shows that here. Okay, so from this we can write equation number 1. You can see that equation number, what is equation number 1 here? Sn is less than or equal to Sm. Sm is a fixed number, plus here k into Tm, this is fixed number, this is a fixed number, plus k into Tn. Now here this number is a bounded B, so this B and this fixed number, we get that Sn is also bounded. This shows that Sn is a bounded. Sn is a bounded. Now it is a positive term series, and we know that whenever the sequence of positive term series is a bounded, then it is a convergent, since it is a monotonic increasing. This is bounded above, and hence Sn is a bounded, so Sn is a convergent, and summation Un is convergent. This gives a convergent sequence. Now see the second part of this, whenever summation Un is not convergent, summation Un is not convergent, that means the sequence is not bounded above. And you can see that here, you can see from this here you can see that from this relation this is not bounded above, so obviously this part is also not bounded above. It is not bounded above means if we have a number g, then the terms of the sequence is obviously greater than g. If this is greater than g, then obviously Tn is also greater than g, and that means Sn is not bounded above, so Kn is also not bounded above. That means, so here we get that Sn is greater than g for all n greater than equal to m0, and this shows that from what is there here, Sn is less than, if we write it as a h plus k into Tn. Okay, so here this is Sn minus h less than k into Tn, and this gives that 1 divided by k into Sn minus h is less than Tn. Okay, so this means that but Sn is obviously is greater than g. Sn is greater than c, so 1 divided by k into g minus h is less than Tn, and hence sequence is not bounded. Tn is not bounded, so summation Un Vn is not convergent, and this proves the first comparison test, and it is a very important test. It shows whenever we have this type of relation Un into KVN, this is a relation, then as Vn is convergent, Un is also convergent, and when Un is a divergent, then Vn is also divergent. Now we see the limit form of this series comparison test. And statement of the limit form of the comparison test is, if summation Un and summation Vn are two positive term series, two positive term series. It is a positive term series such that limit of un divided by vn is equal to L, where L is a non-zero finite number. L is non-zero finite number, then the two series converge or diverge together. So we can see that both the series are positive term series, and obviously we have L is also positive. Limit of positive term is never negative, and hence as limit is given for epsilon greater than 0, there exists a positive integer. We choose a positive number L minus epsilon greater than 0. We choose L minus epsilon is greater than 0. So for epsilon greater than 0, there exists a positive, by definition of limit, there exists a positive integer m such that, what type of integer? Mod of un divided by vn minus L is less than epsilon for all n greater than equal to m. From this we can write L minus epsilon is less than un divided by vn is less than L plus epsilon for all n greater than equal to m. Or from this, L minus epsilon into Vn is less than Un is less than L plus epsilon into Vn for all n greater than equal to m. This is equation number 1. Now just we have shown that whenever Un is less than equal to k into Vn, as Vn is convergent, Un is also convergent. Here we can apply the same criteria. So whenever Vn is convergent, summation Vn is convergent, then you can see that from this first part of this inequality, Un is less than L plus epsilon into Vn. Okay, so this shows that this Un is also convergent. Okay, now whenever Vn is a divergent, then from the second part of this, L minus epsilon into Vn is less than Un. Here we know that as a Un is a divergent, Vn is also divergent. So whenever Vn is divergent, Un is also divergent. So depending on Vn convergent, Un convergent, Vn divergent, Un is also divergent. Now the second part of this, first when summation Un is convergent, consider this inequality Vn is less than Un. Vn convergent, this means Vn is also convergent. Now second possibility, when Un is a divergent, consider this part Un less than L plus epsilon into Vn. Un is divergent, so this shows that Vn is also divergent. So whenever Un convergent, Vn convergent, Un divergent, Vn is also divergent. Here we get the same relation. When Vn is convergent, Un is convergent. When Vn is divergent, Un is also divergent. So therefore the two series converge or diverge together. That means as one series convergent, the other is also convergent according to this limit forms of the comparison test. So friend, I hope you have get the idea of two comparison test. First comparison test of the first type, and second as the comparison limit form of this comparison test.